Let's jump right in. If you're gearing up for your Class 9 science exams here in Nepal, or honestly, if you just want to figure out how the entire universe is glued together, you are exactly where you need to be. We're going to make revising atomic structure and chemical bonding incredibly simple today in this explainer.
So, here's the game plan. We're going to zoom all the way into the inside of the atom, look at how famous scientists modeled it, figure out isotopes, arrange some electrons, unlock the rules of valency, and finally see exactly how chemical bonds form.
All right, let's start at the very center, inside the atom, the literal building blocks of matter. For the longest time, people actually thought atoms were solid, indivisible little spheres. But it turns out, figuring this out was more like a massive detective story. Back in 1886, Goldstein discovers these positive particles, the protons. Then, a few years later in 1897, J.J. Thomson spots the negative ones, the electrons. By 1913, Niels Bohr is mapping out exactly how they move. And finally, in 1932, James Chadwick finds the missing puzzle piece, the neutral neutron. Just a few decades, and our whole understanding of reality flipped.
Now, you'll definitely want to lock this information into your memory for the exam. Think about the mass and the location. Protons and neutrons, they both have a mass of 1, and they are packed tight, deep inside the nucleus. But electrons are wild. They're whizzing around way outside the nucleus with a negative charge, and their mass is so unbelievably tiny that we literally just count it as 0.
Okay, so we've got our 3 particles, but how did we actually figure out how they fit together into a model?
You see, Thomson originally thought the atom was kind of like a watermelon, just a positive blob with negative electrons stuck inside it like seeds. Well, Rutherford totally smashed that idea with his gold foil experiment. He literally fired these super fast positive particles at a ridiculously thin sheet of gold foil. And guess what? Most of them just shot straight through. That blew their minds because it meant the atom is mostly just empty space. A few deflected at sharp angles, meaning they hit a positive center, and a tiny, tiny fraction bounced right back at him. That proved the nucleus is extremely dense but absolutely microscopic.
But Rutherford's model had a pretty glaring issue. If the outside is negative and the center is positive, why don't the electrons just crash right into the nucleus? Niels Bohr stepped up and fixed it. He realized electrons aren't just floating randomly, they revolve in strict, fixed, circular paths called shells. We call them K, L, M, and N. And here's the kicker. As long as an electron stays in its own designated shell, it doesn't lose any energy. It's completely, perfectly stable.
Moving right along, how do we actually identify these individual atoms? Let's talk numbers and isotopes.
Now pay attention here because this is a classic exam trap. Isotopes versus isobars. Isotopes are atoms of the exact same element, like carbon, but they have different mass numbers because they have extra neutrons. Think of them like identical twins, except one just had a huge meal and is a little heavier. Isobars are the exact opposite. They are completely different elements, like argon and calcium, but they just so happen to weigh the exact same amount.
So we know what's in the center. Let's head to the outside and arrange those electrons.
Just like a classroom has a strict limit on how many desks you can cram in, atomic shells have a seating capacity. And your golden formula for this is the 2n squared rule. It's super simple. The K shell is the first one, so n equals 1. 2 times 1 squared is 2. Boom, K holds 2 electrons max. The L shell is number 2. 2 times 2 squared is 8, so L maxes out at 8. You do the same math and you get 18 for the M shell and 32 for the N shell. Easy, right?
But wait, nature throws a massive curveball here. It's called the octet rule. Even if a shell, like that third one, is mathematically big enough to hold 18 electrons, if it happens to be the very outermost shell of that atom, it enforces a strict speed limit. It absolutely cannot hold more than 8 electrons. Why? Because the universe is fundamentally lazy. Everything just wants to relax into a superstable, low-energy state. And for an atom, having exactly 8 outer electrons is peak stability. And because atoms crave that stability so much, we have to talk about valency, their combining capacity.
Atoms will basically do whatever it takes to get that magic number of 8 in their outer shell. Valency is literally just the number of electrons an atom needs to lose, gain, or share to get there. It's just a simple if-then game. If an atom has 1, 2, or 3 outer electrons, it's so much easier to just chuck them away, so its valency is simply 1, 2, or 3. If it has 5, 6, or 7, it's much easier to just steal a few to get up to 8. Just subtract from 8, and there's your valency. If it's got exactly 4, it's a sharer, valency of 4. And if it already has 8, it's perfectly happy, unbothered, and does nothing. Its valency is 0.
Which brings us beautifully to our final section, forming chemical bonds and exactly why these atoms combine in the first place.
Really think about this for a second. If individual atoms are usually incomplete and unstable on their own, what do they absolutely have to do to survive?
They have to team up. They form bonds to find stability, and they generally do this in 2 totally different ways. First up is the ionic bond. This is all about a complete transfer. A metal atom just straight up gives its extra electron to a nonmetal. The metal becomes positive, the nonmetal becomes negative, and since opposites attract, they lock together like supermagnets. The second way is the covalent bond. This happens between 2 nonmetals. Neither wants to give up an electron completely, so they compromise. They mutually share their electrons so they both hit that magical, stable octet.
And when these nonmetals decide to share, they don't have to stop at just one pair. If they share one single pair of electrons, that's a single covalent bond, like you see in a hydrogen molecule. But if they're really hungry for stability, they might share 2 pairs, creating a double bond, like the oxygen we're breathing right now. And they can even go all out and share 3 pairs to form a super strong triple bond, like in nitrogen gas.
Now, because these 2 types of bonds are built so fundamentally differently, they behave entirely differently in the real world. Ionic bonds are like those super strong magnets we talked about, which means they form hard crystals, have crazy high melting points, and they can conduct electricity when you dissolve them in water. Covalent compounds, though, they're just sharing. The hold is a lot weaker, so they have low melting points, usually won't dissolve in water, and they definitely do not conduct electricity.
You know, this stuff isn't just theory to memorize for your class 9th exams. Literally every single object you can see, touch, or hold right now is glued together by these completely invisible forces. Think about it. The water you're drinking, covalent bonds. The salt you sprinkle on your food, ionic bonds. So, as you walk around today, take a look at the world around you and ask yourself, which of these invisible bonds is holding your world together right now? Good luck with your revision. You've totally got this.